Sir, am I audible? Hello, am I audible? Sir, am I audible? Hello. Hello. Hello.
Hello everyone. Very good evening to you. We will continue. with today's session. First, discussing last week's assignment questions and then trying to solve some problems out of the current week session. So let's wait for some time to see if somebody else joins. Then we will start. Okay?
Hello, am I audible, sir? Hello?
Yeah, please, you are audible.
Yes, sir. I have three doubts. Actually, in assignment number 6, you have solved three questions wrongly, sir. I can give you the proof. Can we discuss with each other?
Yeah, go on.
Okay. May I share my screen?
I think that is not permissible, but you can ask me about which question you are having
Okay.
doubts with.
Okay. Can you share assignment number 6 that you have already thought in previous recording? You have the doc. If you have the document, you can share the assignment number 6 questions.
You can go on asking what question. I have that in open. I can't open that right away because the session is being recorded and it has to be current week's question only.
Sir, one question was based on resistance welding process. The question is this: in a resistance welding process, the applied voltage is 10 volt. Determine the rate of heat generated per unit area with 20 bridges per centimeter square, each bridge having radius of 0.5 mm. The resistivity of the material is 15 into 10 raised to power minus 5 ohm centimeter. So question number 8.
Yeah, go on.
Question number 8.
Yeah, go on. What's your doubt?
Okay, sir. First of all, if you have calculator, then calculate the value of resistance RC. Please calculate.
You tell me what value you have got and what is your problem?
Sir, is it right value or wrong value? Please calculate it.
You tell me. I am asking you. You tell me what value are you getting? What is the mismatch? What is your query?
Sir, I am getting 1.35 into 10 raised to power minus 4 ohm centimeter square.
Okay. And the
1.3.
answer was
And answer is okay. What the mistakes is this? You are calculating the rate of heat generated per unit area by Q is equal to N by RC.
yeah.
N by it is not N by RC. It will be V square by RC. If you are taking N by RC, the unit will be watt per centimeter square.
Mm-hmm. Okay.
Is it possible that the heat rate of heat generated will be in watt per centimeter if we will substitute the value of N?
Yeah, that's right. Yeah.
So this question is totally wrong, sir.
So did you get any clarification from NPTEL regarding this?
Sir, I have already mailed to NPTEL team as well as in the discussion group. So they are saying
Okay.
the question is right. The question is right. So please, I have requested you, please contact or you can talk to the NPTEL team and please tell them that the question number 8 is wrong.
So you have
So
been graded, you have received the gradings already, right?
sir, I have got 0 marks in this question because every option is wrong here. So I have choose that in which 10 raised to power 5 is there. I have choose first option because
Hmm.
no option were correct in this. So I need to choose one of them. So I have choose A, but the options 4 options are wrong.
Okay.
Okay,
Okay, don't
and the
worry. If your answer is right, then it will be clarified and will be given marks for that.
okay,
So
and
I
huh?
don't have the authority, but I can forward your query to the NPTEL team. Okay.
Are you agree with me? This solution is incorrect.
Yeah, if you use N, then it should not be the unit should not be
What?
right.
Yeah, yeah. Okay. So you got my point. Actually, I want to talk to Professor Shantanu Bhattacharya. Is it possible or not?
No, that won't be possible.
Okay, so you can inform. And question number 9 is also wrong, sir.
Question number 9. Can you tell me the question?
Question number 9, the tool has life of 180 minutes at a cutting speed of 18 meter per minute. If the tool life is reduced to 45 minutes, then the cutting
Yeah.
speed according to the Taylor's tool life equation, sir. Is it
Okay, so what's the problem?
this? The correct answer will be 36.
Okay. And what was there in the assignment?
Sir, if you will substitute the all the value, you will get 36. Here, the right answer, as per the NPTEL team, the right answer is 72, but it is wrong.
Okay.
It is totally wrong. So if think, if you will calculate the value of C, calculate the value of C. We take V1, T1, and N. Put the value of V1, T1, and N. Calculate the value of C, and uh, and in same procedure, if you will substitute V2 as 72 and T2, which is given as 45 minute, and put the value of N and calculate the value of C, the C will be different in both cases.
Yeah.
So if you will substitute 36, the C will be same.
So what are
I,
you getting? You're getting 36.
36, yes, 36 is correct. You can just equate V1 T1 raised to power n is equal to V2 T2 raised to power n, and substitute all the values and find the value of V2. You will get 36.
So what you can do is, whatever problem you are having, have you written that in the discussion forum?
Yes, sir. I have already mailed as well as written in the discussion forum. So they said that the solution is correct, but the solution is totally wrong, sir. Is
And
it?
what they replied, it is correct.
Yeah.
Okay.
So you can, sir, you can calculate the value. You will get 36.
Okay. So okay, I will. And what is the third question you are having doubt about?
Yes. Third question is, sir, question number 5. Which of the following is an important factor in solid phase welding?
Hmm.
So the important factor, it is asking about important factor. So important factor are A and B. Surface deformation is very important in solid phase welding, and recrystallization is also very important in solid phase welding. The type of bonding is not an important factor. If the question is just like which of the following is not an important factor in solid state welding, then the type of bonding will be the correct answer. But here, the option A and option B both are correct. But we need to choose one, because there is restriction to choose one option.
Yeah.
So it is totally wrong, sir. So type of bonding is not an important factor in solid phase welding.
So okay, you got a reply to this in the discussion forum.
Yes, sir. Someone, I think someone mailed, and yes, I have got, and they have mailed me that we have re-evaluated the assignment number 6, and they have just, because they have given two same questions, so just they have considered only 9 questions, but they are saying the questions, the solution of these three questions are correct, but it is not correct. You can, sir, talk to the NPTEL team, and you can please inform that these three questions are that the solution of these three questions are wrong. And if you will if you will tell them, then it will help in final exam, because in final exam, if they will give us the wrong question, then definitely we will going to reduce our mark.
No, don't worry. If the question or if the answer solution which is the answer which is given in the solution is wrong, then it will be taken care of. Don't worry. And
Sir,
I will forward your query.
so sir, are you agree with me that these three questions are incorrect?
Yeah.
Okay,
I
sir. So
think that solid state welding question that is arguable, but the other two questions must be
sir,
given marks for that.
I am I am very sure. And if you will go through the lecture which is given by the Professor Shantanu Bhattacharya, you will find that I am right.
Okay, don't worry. I will forward your query to taken care of. Okay.
Okay, okay. Thank you, sir.
Okay, so proceeding with today's plan, let us first look at last week's assignment questions. Okay. So the first question you had to answer about some of the theories, deformation theories. There are, broadly Tresca's and von Mises theories you are already acquainted with. Now the question asked, the first blank is same for all the options. Okay, so you had only a Tresca's criteria, and then Tresca's yield criteria explains what kind of flow will take place. Now you all know that beyond the yield point, there is only plastic deformation. Okay, so the second option then goes for plastic, and then it says when uh, the load stress exceeds the critical value. Now, because principal stresses are dealt by von Mises theory, so in this case, you have the maximum shear stress uh, being the uh, third option here, third answer here. Okay. The Tresca's yield criteria explains plastic flow will take place when maximum shear stress exceeds the critical value. Now, the second question was about choosing one of the options for metal forming processes. So, so metal forming, is related to changing shape of the metal through some external force or pressure, right? So, option C, you can relate to the diagram that first option is a wire drawing operation, second option is a forging operation, third option is an extrusion operation, and fourth option is a 2 mill high rolling operation. Okay. So drawing is when a workpiece is drawn through a die. Forging is when a workpiece is pressed between two dies. Extrusion is when a metal substrate is pushed through a die by a punch, and rolling is when a workpiece is processed through two rotating rolls. So there can be other kind of rolling also, but as per the diagram is related, so you have the rolling process with two high roll mills. Okay. The next question was metal forming is caused by what kind of effect of the workpiece. So you all know plastic deformation is the main reason behind any uh, metal forming or change of material shapes, right? So that plastic deformation should be the answer of this question, and other options are wrong. Then which of the following is a type of extrusion process? So you know there are direct extrusion processes, indirect and hydrostatic extrusion processes. So in this case, option B comes within the boundary, within the limits of extrusion processes. So there are multiple types, as I said, including cold, hot, direct extrusion, impact extrusion, hydrostatic extrusion, okay, friction extrusion. So option A is frictionless here, so that again goes wrong. Option B is the correct option. So process for making wires of metals is called as drawing. Right? So of course, uh, if it was extrusion, then you should have got slab as the other option, other answer here. So because there is no such combination, so you have wires and drawing. Option D is the correct option. Next question was for establishment of yield criteria. It is assumed that metals are homogeneous and isotropic. Right? We have discussed that in the beginning of last session elaborately. You can please have a look if you have doubt on this. So there are two assumptions. First one is considering the material as homogeneous and isotropic for the establishment of yield criteria. And then in a rolling process, the two rolls must rotate in opposite direction. Otherwise, if they rotate in the same direction, then it will be difficult to actually draw or pull the sheet within the two rolls. So option A is again the correct option here. Okay, then you have deformations of a solid are observed. At which point, so you all know that after yield point the plastic region starts, so no such combination is there. So option D, where elastic deformations of the solid can be observed before yield point, is the correct answer. The next question is what will be the true strain in a material specimen if it is stretched from one length to another. So you all know how to find out true strain. So if you put the negative sign, then it comes natural log of final deformation to initial deformation. Just plugging in the values of final deformation is 25 centimeter and initial is 17.5. You can find, you can see that option C minus 0.357 will give you the correct answer. The last question was here. We have extensively solved much bigger problems from this kind of concepts, flow stresses and strains. Okay. And then here in this question, it was a simple solution. You have to find out the final true strain and flow stress. Okay, when the average flow stress is given as 493 megapascal. Okay, strain coefficient is 680 K, and the strain hardening exponent is 0.25. So you know when there are plastic deformations and there are non-linear strains that a material experience. So in that case, average flow stress is given by the ratio of K, strain coefficient K, epsilon strain to the power strain hardening exponent
Sir,
n divided by 1 plus of strain hardening exponent n. So just plugging in the values, okay, where strain coefficient is given as 680, strain hardening exponent is given as 0.25, true strain is given as 0.675, and the flow stress then becomes A epsilon raised to the power n, so it is 616.25 megapascal. Okay.
sir, can you show me the previous question?
Yeah. This one?
Yes, yes, yes. Sir, in this true strain can be negative or positive because it is stretching from
So
smaller
if
value to
you
larger.
if you put the plus sign, then it should be it is by default negative if you use the final length in the numerator.
It because we are stretching, so it will be tensile or it will be compressive.
No, that's a different thing. So when you if you can, I think we have derived it in one of our classes. So this is a standard formula that and then when you do this, if you remove the negative sign, then the initial dimension should go in the numerator.
Sir, what is how we can calculate? We need to just integrate from lower limit to higher limit, and if we will integrate, then we will get positive, I think. How we can calculate true strain? What is true strain?
So have you solved it?
Sir, I am getting positive answer. That is why I am asking.
No, it should be negative. In further query, if you have further queries, please write it there, and the NPTEL team will clarify. So now we'll be moving ahead to solving some questions out of the current text content. And I think you have come through this single crystal growth process called Zrokalski process. This question is based upon that Zrokalski's single crystal growth process. So you have crystal growth process of silicon with a temperature of 25 degrees centigrade. Convective heating is utilized here to melt silicon at 1400 degrees centigrade. So you have to find out the pull rate of seed through a fusion zone of 100 centimeter thickness. If heat conductivity of silicon is 2.3 watt per centimeter Kelvin, and the latent heat of fusion of silicon is 1787 kilojoule per kg. So you can take the density of silicon as 2.33 grams per centimeter cube. Uh, just to give you an idea, you must be aware about Sokalski's process, where we put in a seed in a chamber where inert conditions are maintained, and then as the seed is rotated and pulled out, the melt silicon is simply gets attached or linked to the surface of that seed, and as it is pulled out, we get the solidified uh, silicon material. Okay, now uh, one problem that arises is some extra material also gets sticked, and that needs to be removed after the process is completed. Now, in this question, such a process has been shown, and you have to actually find out the pull rate of the seed. Okay, and you have to relate the pull rate to the thermal gradients depending upon and plug in all the data which is provided to actually get the solution. So give it a try and then we will see how to solve this problem. So, Nutan, can you hear me?
Yes, sir. Yes, sir. Yes, sir.
So I just had a chat with the NPTEL TA for this
Okay.
question. Now, in this question, you are saying the minus sign should not be there, right?
Yes, sir. Why?
Otherwise, the magnitude is correct.
Yes. Magnitude is
So,
correct. Magnitude is correct.
so for your information, like if if the wire or a metal specimen or something stretched,
Okay.
so the stretching can happen in the longitudinal direction, right? But
Oh,
when a material is being stretched in the longitudinal direction, it can automatically be compressed in the lateral direction, right?
yeah. Yes.
So in that case, if somebody is talking about the longitudinal strain, then it should be positive. If somebody
Yes.
is talking about the lateral strain, it should be negative. So here in this question, they didn't specifically mention if it is longitudinal or lateral, what type of strain they're talking about. So you try, if the magnitude is right, then you will be uh, avoided. Okay?
Yes. Yes. But in some lateral direction, there will be minus mu sigma by E. That will be the strain.
Yeah, that's not clear in this question. So might
Yeah.
be they have modified the question, and during modification, the sentiment was not clear.
Okay, sir. Okay.
Just if the magnitude is right, then we will be awarded.
Yes. Yes, sir. But sir, please inform that three question also.
Yeah, don't worry.
Okay.
But the
Thank you.
solution has already come out, no?
Sorry, sir.
The solution has already come out.
Sir, your voice is coming not clearly. What are you saying, sir?
I am saying for the three questions from assignment six, I think you are asking, right?
Yes, 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 sir. Yes, sir. Yes, sir.
And why didn't you not mention those in the last session? Because by now, I think they have already graded that assignment.
But sir, it can be changed, sir. It can be regraded, sir.
So regrading has also been completed, no?
But sir, I have mailed them. I have not informed you, but I have mailed them. But they have not changed the grade, and they. I think they have thought that their solution is correct. But but I can clarify with discussion. So I thought that I should join this live meet, and I will inform you, and you can contact to NPTEL team, and you can inform them.
Okay,
But I
no,
want.
don't worry. I will forward it. Don't.
Okay.
So let's look into this question of single crystal growth process. It is a simple concept. You just have to think about what will be the heat transfer process which will be happening while the seed is being drawn out of the melt pool. Right now, you have to just equate the total heat transfer loss to the total heat transfer gain. Yeah, so if you just think about this rectangular part in the top of the screen, you can see being the seed, then the one side of the seed is connected to the molten melt side, and the other part is the top side is connected to the ambient, right, where solidification happens. So if Q1 you can think be the heat transfer rate in the melt pool side, and Q2 be the heat transfer rate in the ambient side. So in that case, you have temperature T1 in the melt pool side and T2 in the ambient side. So automatically T1 should be greater than T2. So T1 being towards the melt pool side, and then you just so you know that the total net heat transfer rate, just you use the Fourier law to find out the net heat transfer rate and equate it to the total energy transfer in case of phase change, which is given by latent heat of fusion multiplied by the mass flow rate, which is dmdt. Okay, so in that case, so K stands for conductivity, A stands for the area, and dt dx is the thermal gradient. So the coefficient L stands for the liquid melt side, and S stands for the solidifying, the upper ambient side. Okay. So you just equate the total heat transfer rates, and then you break down uh, dm dt, mass flow rate m, into rho density multiplied by av, okay, area and velocity. So then you just rearrange that to find out the density multiplied by latent heat multiplied by area, and then velocity, which is dx dt, or being equal to, because to maximize the total heat transfer, you can simply see from that equation and the second equation in the screen that the liquid side total heat transfer rate should be 0. So just for the maximum LHS and the RHS part, the liquid part of heat transfer KL A dt dx should be 0. So just considering that to be 0, you can simply find out the Vmax as dx dt equal to Ka by L dt dm, and from that rearranging, you can find dm dt, which is the pool rate, metal pool rate, equal to K by rho L and dt dx. So once you find out this rearranged formulation, you just plug in the values where the temperature difference is given by Tm and T naught difference, which is 1375 degrees centigrade. And then you can from the question, the total distance dx is around 1 meter. Thermal conductivity K was given there as 2.3 watt per centimeter Kelvin, and then it just convert it to meter kelvins and multiply it by 100, and then you have the latent heat of fusion as 1787 kilojoule per kg. Okay. And then you have the density is 2.33 gram per centimeter cube. If you convert that to meter cube, you have 2330 kg per meter cube. Okay. So just plugging in all these values, you can find dmdt as 9.1 to 10 raised to the 5 kg per second. So that is the metal pool rate which was asked in the question. Just take a note of this, and then we'll proceed to our next topic. Okay, so moving ahead to the next topic, we will talk about something called edge selectivity. Okay, so before coming to this question, let us first see what edge selectivity means. Now, this is something out of your microfabrication processes, which is an integral part of today's manufacturing industry when it is coming to uh, any electronic devices or semiconductor devices industries, right? So their etching is a bread and butter of their daily production process. Okay, so now something called edge selectivity is a critical part of that microfabrication processes. So edge selectivity is something which defines how much of the part which is required to be etched is actually etched and how much is over etched. Okay, so if you look at this diagram in the top right corner here, you can see that in the first diagram there are two certain conditions which are shown here, right? So in the first diagram you can see that uh, the bottom part, okay, the bottom part, the green color bottom part of the particular slot is being a little much of over etched, right? And then as compared to the second situation. So this is what is being defined by edge selectivity. So edge selectivity is something which is defined as the ratio of the etch rate of the bottom layer, okay, where you can take this as D2, which is the dimension of the bottom layer, and then etch rate of the mask layer. Okay, something which is masked, you don't want that mask layer to get etched, right? So that is the overetching region, overetched region. So D1, if it is the masked region, you can see in the schematic diagram here after reactive ion etching. So you can look at the D1 dimension and D2 dimension. So selectivity is defined as the etch rate of the bottom layer to etch rate of the mask layer. In these two situations shown in the diagram in the top right corner, so in the first diagram, you can see the edge selectivity is really poor. Okay, it is low edge selectivity. So what is happening is the bottom surface is getting over etched. And in the second situation, you can see a comparatively better edge selectivity. So, or you can say it is a highly selective etching process which has been followed. Right? So low edge selectivity gives rise to poor etching, and high edge selectivity gives rise to good etching. Now let's come back to this question. It says substrate damage is more when edge selectivity is what? So as per our discussions, so substrate damage will be low when edge selectivity is low, right? So here the answer is wrongly marked as red. So the option A should be correct one here. Substrate damage happens to be more when edge selectivity is low. Okay. Now let's look into a question out of this. So microchannel is being etched in a 100 planar wafer with K-weight solution. You have to find three answers. First one is you have to determine the angle between the channel wall and the front surface. Okay. So here that particular angle is defined as alpha. If you look at the diagram, the first diagram, it is the angle between AB and BC. For your hint I'm giving, that is the angle between the channel wall and the front surface. And the second question is if the top channel and the etch rate are 100 microns and 1 micron per minute. So the top channel length is 100 microns and the etch rate is 1 micron per minute. Then you have to find out what is the bottom channel width after 20 minutes of etching. So if you can find the top channel width, you can easily just do geometrical calculations to find out the bottom channel width. And the last question is how long will it take until the etching process stops? So the total time of etching you have to find out. So give it a try and then we will discuss the solution. Okay, so let us look at the solution to this question. I have just enlarged the part which is being asked in the question. So the angle between the channel wall and the front surface for your perusal here. So AE is a 100 plane, and then AC is a 010 plane. So using simple tangent angle, you can find the length of AB be root 2 by 2. Okay, or you can say 1045 is 1 by root 2, so that is root 2 by 2. And AC here is 1, okay, which is given in the question. So you can find out the angle simply through geometrical calculations as tan inverse of AC upon AB. That will give you around 54.74 degrees. The second question was to find out after 20 minutes of etching what happens to the bottom channel width. Again, I have just shown you pictorially which part it is being asked about. So the bottom channel width. So the top channel width is given as 100 microns. You can see from the diagram. The etch rate is given as 1 micron per minute. Okay, and then if you consider that portion unknown length as d, okay, so the d can be found out as the etch rate, okay, which is given as 1 microns per minute multiplied by the total time of etching, which is 20 minutes. Okay, so if you multiply that, you can find the value of d to be 20 mm. Right now, there are two symmetric lengths y in both sides between which is the difference between the top width, top surface width of the channel and the bottom surface width of the channel. So you can find out y as as d is dimension d upon tan of alpha, right? So when you have found out alpha as the angle between AB and BC, that angle becomes equal to the angle which is subtended by that triangle with an altitude d, right? So y can be found out as d upon tangent of that angle alpha, and you can find out the bottom length of the channel L bottom as L of top minus twice of that symmetric difference in length between the top and the bottom width y, okay, which is again d by tan alpha. So just plug in the values of alpha, you can find out the bottom length is 71.7 micron. So again, just uh, we have the third question, which is how long will it take until the etching process stops? So now you know L bottom, right? And then you have to refine L bottom so that it is you can find out the maximum stretch of the etching process so that you can find out the time when the etching process stops. Okay, so in that case, you have to find out the maximum D, right? So D max, then from that equation, you can see you just have to reshuffle. You just have to do what happens to the maximum H when L bottom becomes 0, right? So then you have L top minus twice of D tan alpha, D upon tan alpha is 0. Just reshuffle and find out D max to be 70.71 microns, right? So once you have found out D max, you can simply find the time by dividing it upon the H rate, right? So, time is found out by distance upon velocity. So here the D max becomes the maximum distance of etching, and when Dmax becomes full, so the bottom channel is not there, right? And the bottom channel length becomes 0. So in that case, you can find out the time of etching at which the time at which etching stops. That is when the process is completed and there is nothing to etch in that hole. So it is a through hole. So that time you can find out by Dmax upon the velocity, which is 1 micron per minute. That will come out to 70.71 minutes. Just take a note, and then we will proceed to the last topic of today's discussion, which will relate upon to the photolithography process, which is an integral part of any microsystem fabrication industry. Okay, so we have reached to the last topic of today's discussion. So now we will discuss about the photolithography process. Okay, you know that is an integral part of micro manufacturing. Whenever you are making PCB boards, you are making uh, any because the miniaturization is the need for today's industry, right? To save space and increase the output. Now, any fabrication of such sort, photolithography is one of the most important processes, okay, of micro nano manufacturing industry. We'll, uh, we will briefly look at what the photolithography process is. So you start with, there are three major steps. First one is the positioning step. Okay. So it is where you decide the optimal distance between the mask and the substrate. Now that is very important because you know what is photolithography first of all. So photolithography deals with positioning. Photolithography deals with positioning a mask, okay, in which there is a pattern which is pre-inscribed, and then using that mask, you exposed some part of the surface, substrate surface, to the incoming uh, light, which may be a UV laser or a LED laser in advanced photolithography equipments. And then you decide, depending upon what kind of coating material you have put on the substrate. Right? So you first coat the substrate, okay, with a material which are called as photoresists. And depending upon the nature of the photoresist, you decide upon the mask. Okay, so you don't if you don't want the masked region to be waved off after you complete the patterning process and do the removal, maybe which is called as the lift off process or the developing process. If you don't want the masked region to go away, then it is called as the positive photolithography process. And if you actually are looking to remove the masked region and just bond the exposed photoresist to the substrate, then that is called as a negative photolithography process. So you have three options, three steps: positioning process, exposure process, and developing process. Okay. Now, defining photolithography in one statement. So photolithography is a process, okay, which is used in the manufacturing of integrated circuits, as I told you. And then it involves using light to transfer uh, a pattern, which we just discussed, how to transfer the pattern depending upon the nature of the photoresist, which has been pre-coated on the substrate surface. Uh, we use light to transfer that pattern on the mask into the substrate, which is generally a silicon wafer. The process begins with a photoresistive material, which is called as a photoresist, and there are positive photoresists and negative photoresists, and then being applied to the substrate. Okay, so that happens to be the proper definition of photolithography process, and then we have three steps. First one is positioning. So you have to position the substrate and the mask such that these are at an optimal distance. So I'm not saying the minimal distance or I'm not saying the maximum distance. It should be an optimal distance. So optimal distance as in the incoming light which is striking the surface should not get diffracted, so that your pattern actually is not exactly transferred and you get a deformed pattern on the substrate surface. So that distance should be optimal, right? And then you have the exposure process, in which the incoming light, maybe an UV laser or an LED these days, uh, strikes the surface and just inscribes the pattern on the mask into that substrate surface. And then you have the developing process, in which you remove the unwanted photoresist and just get the pattern transferred to the substrate surface. So there are two kind of photolithography processes, positive and negative. So you can look at the positive side where you have a substrate, you coat it with the photoresist, and often you use an adhesive promoter between the photoresist and the substrate surface just as to so as to improve the bonding process. And then you just transfer the pattern in the mask onto the resist surface. Okay, so you can see here in case of positive photolithography process, what happens is the masked region stays and the unmasked region washes away during the developing process. While in case of negative photolithography, you have just the opposite. Okay, after step 3, it remains same, and in step 4, the exposed region stays back because of bonding, strong bonding cross-linking to the substrate surface, and the unexposed part, because of weak bonding, washes away during the developing process. So that is a briefing about the photolithography process. And if we just look into the detailed steps, you have the first substrate cleaning in order to remove any kind of dust or undesired particulate matters over the substrate surface. You clean that often with Pirana solution, and then you dry it up, maybe through compressed air or compressed nitrogen flow, and then you do the spin coating process through a spin coater. Okay, what you spin coat? You spin coat the photoresist material, and then you do the pre-baking to make sure that the cross-linking has happened nicely, and you do the exposure process where the light strikes the coated substrate surface. You do the post baking again to make sure that there are no loosely cross-linked structures in the desired region, and then you do the developing process where the undesired material is washed away. You again do the hard baking process, and you do the etching often if you want maybe to etch some material out of the substrate. Suppose you are doing positive photolithography and then you have done the developing process where the material has been washed out of the undesired region. Now, in those regions, the substrate is exposed, right? And in the masked region, the substrate is unexposed because the photoresist coating has stayed back. Now, if you want to transfer those patterns into the substrate surface, the uncoated or exposed substrate surface, you do the etching process. Okay? So what happens? You will just have the circuitry, maybe for example, inscribed into the silicon surface. Now you do the strip off or lift up process in which all the photoresist material is washed away and you have the pattern simply inscribed into your silicon surface. And that completes the process. And then you do all the wirings and connections through processes such as wire bonding or wiring. So after that, the device becomes gets fabricated and you can integrate it to the different parts and components of the particular application you are looking at. So that somehow completes the photolithography process. I hope you have got an idea. If so, then we will start today's session. Again, for the doubts you are having in your assignment questions, you can please clarify here or just for discussing and just getting what is the right answer. And then for the grading part, you have to write to the discussion forum and mail there. I can help you reach out to the NPTEL team uh, for the questions, for the queries I got today. I will forward it. Probably will get an answer. So, all right. So I will stop here. If you have any doubts, you can go ahead.